What is the date today? Good. Welcome back. I hope everybody had a good spring break. Kind of the theme, what we're doing now. Oh.
Sorry, you got a big old air thing.
A big old what? Oh, that's annoying. Give you a brief reminder. So you're working in your lab. You're collecting some data. So you get these data points. So maybe X is the height you drop something from, and Y is the time it takes to fall. Or X is how much of a certain chemical you add, and Y is the yield in some chemical process. And in theory, no, so if you graph these, there's 3, 2, there's 4, 3. In theory, these should all be online. Okay, but the idea here is the observed data is always the real data corrupted by some noise. So this could be measurement error. This could be maybe the model assumes there's no humidity, but so external factors. Who knows why we get the noise? So we're given the observed data, and we want to somehow extract what the real data is based on the observed data. So here's the theory. We use linear algebra to say what most likely the real data was. Okay, so there's some line here. So maybe this is the real data. And then we just get these deviations from the real data because of the noise. Or maybe that is the real data. Who knows? Linear algebra will make this problem precise, and we'll extract out what that line should have been. So here's our observations again. Okay, so. If the data are all unaligned, that they would satisfy the equation y equals mx plus b for some values of m and b. So each of these data points I can use to make an equation. Just plugging the x and y values into this. And let's change this into a system of equations. Rewriting it a bit, this looks a lot like the systems of equations that we saw in chapter 1. So let's do that. The obvious and pleasant thing is going to happen. The reduced row echelon form of that matrix looks like this. That bottom line tells me that 0m plus 0b is 1, right? Good. No solution here. So in chapter 1, we stopped with, so in chapter 1, we said there's no solution to this system of equations, and we stopped there. Now, we will find the best non-solution. So some non-solutions are going to be better than others, and we're going to figure out, or we're going to say exactly what, we're going to score the non-solutions and talk about how to pick out the best one. Okay, so. Here. Was it? I know. These are my lecture notes. So got our data again. And what I think about a non-solution as doing, a copy of this. Is do it this way. So for the non-solution, m equals 1, b equals -1, it says that the line that would fit the data is y equals x minus 1, which isn't going to work. We'll see how close it is. And for this m equals -2, b equals 4, the line is y equals -2x plus 4. Actually, you know, let's do it. Let's do it this way. Let's try 2 and -4. Okay, so what I'm imagining is this is a predictor of y given x. So if we use the y equals x minus 1, then the predicted y would be 2, 3, and 4. And the actual observed values were 2, 3, and 1. So got these two right and didn't do very well on this one. Here, there's the observed y. And in this case, the predicted y is 2. 8 minus 4 is 4, and 6. Okay, do you have an intuitive feel for which one is better? So we're trying to predict 2, 3, and 1. This m and b predicted 2, 3, and 4. The second m and b predicted 2, 4, and 6. Okay. To me, this one seems better. Okay, so here's the idea is we can think about this is, so that 2, 3, and 1 is our goal. This is a vector in R3. And so the picture here is the predicted value is 2, 3, and 4. So we're in R3, got that X, Y, and Z coordinate system. And so we've got our goal vector that we're trying to get to. And our prediction function gives us another vector. So I just think about this. So error is actual minus predicted. So predicted is no error plus predict rate. So we're going to go this way. This is how we're going to measure the error. And I want to emphasize that these are all vectors. So given an m and a b, we can make the predictor y equals mx plus b. And then we define the error vector to be Yeah, let's forget which way this goes. Yeah, oh, it's going to be the goal vector minus the predicted vector. And yeah, the smaller the error, the better the predictor. So the best predictor is the one that minimizes the magnitude of the error. Okay, so let's look at each of these. Yeah, just redo them. So m equals 1, b equals -1, x. Yeah, 3, 3, 4, 5, 2, 3, 1. So y is x minus 1 here, 2, 3, and 4. So the observed vector, collecting those measurements together, is 2, 3, and 1. The predictor predicted a 2, 3, and 4. So the error vector for this predictor is that. So just a little bit. And this is all review from last time. And let's do it again. That's what we have. M equals 2, b equals -4. See, 6 minus 4 is 2. 8 is 5. Let's see. 8 minus 4 is 4. And this is 10 minus 4 is 6. So for this one, that's what we observed. So the error is 2, 3, 1 minus 2, 4, 6, 0, -1, -5. And the magnitude of the error then is square root of 26, which is 5 something. So that m equals 1, b equals -1. The magnitude of the error vector is 3. For m equals 2, b equals -4. The magnitude of the error vector is square root of 26, which is 5 point something. So this one had the smaller error. So m equals 1, b equals -1 is a better non-solution than m equals 2, b equals -4. Okay. So the idea is for each non-solution, we can give it a score. We can say how good or how bad it is. So you can quantify that. And then our goal is to find the non-solution that minimizes the magnitude of the error vector. Just want to talk a little bit more about that. So let's go back and grab our observations. Okay, so we saw we can, if we had a line that fits the data, it would satisfy this system of equations. And in chapter 2, so chapter 2, we had the AX equals B form of a system of equations. Okay, and remember that this notation is telling us to take a linear combination of the columns. So what we're trying to do is produce 2, 3, 1 as a linear combination of these two columns. So the column space of this matrix is a two-dimensional subspace of R3. So I want you to think about this. So you're in three-dimensional space. Here's the column space of the matrix. And our goal here is to get to 2, 3, 1. So the outputs of this matrix, Peru is calling me. So the output of this matrix is going to be some vector in the column space. Saying that the system is inconsistent says that the target vector we're trying to get to is not in the column space. But as we talked about earlier in this chapter, so if this is the B vector, this is the best we can do is to solve the system AX. That's projection of B onto the column space of A. Okay, so you could do this with the tools you have already. So method one is factor A into QR, use Q to build the projection matrix, project B onto the column space of A, and solve AX. Okay, so that you could do already. Method two will be, let's call this another way to do this. Okay, so this will be using some of the ideas that we've had before. So there's my B vector. That's my target that I'm trying to get to. I'll never get there because the outputs are always constrained to the column space. So there's the parallel park. Okay, and here's the key is we talked when we were doing the Gram-Schmidt process, we talked about the part that's in the orthogonal complement. So what we have is we break B down into its projection and its the rest of it, but we need to get there. So this is in the column space of A. And this one is in the column space of, or the orthogonal complement of the column space. And we talked about how in chapter 3, I think it was chapter 3 or 4 anyway, recently, that the orthogonal complement of the column space is the null space of A transpose. So in other words, here's an interesting fact. I'll call it a useful fact. Is if we do the transpose of A applied to this part, we get 0. So watch how we can exploit this. Okay, so let's put it all together. So we're given AX equals B, a system of equations with no solution. The best non-solution is the one that solves AX is the projection. That's going to minimize the error vector. So this minimizes the magnitude of the error vector. Okay, so this is where it gets clever. So focus on X. So if AX is B perp, then AX is B minus or B parallel. So remember, B is the projection plus the complement. Which tells us just some algebra. Whoops, rearranges it. Let's do it this way. Okay, so now I'm going to take this equation a transpose on both sides. So A transpose A is A transpose B minus A transpose B perp. Okay, this is the zero vector. And we get this system of equations. Okay, and so the punchline is X solves AX equals. So that's the solution we want. That's equivalent to saying that X solves A transpose AX is. So the solution to this system of equations is the same as the solution to this system of equations. And we can construct this system of equations from our original system. Okay, so let me show you how this works for our particular example. I'm going to do it all the way from the given data. Okay, so there's our data. So our data gives rise to a system of equations, which we can write in matrix form. So I'm going to do it abstractly. Best non-solution solves A transpose AX is A transpose B. Okay, so that's my given system. Let me write it down again, make some room. Multiply both sides by the transpose. Let's see. This would just be the square of the magnitude. Oh, 3, 4, and 5. That's not bad, right? So that's 9 and 16, 25. That's 50. This would just be the sum. So that's 12, 12, and 3. That's 6 and 12 is 18. If I did this right, this is the sum. 6. You've got a system of equations in matrix form. Talked about this in chapter 2. I can just move the matrix to the other side of the equation, put an inverse there. Cheat a little bit. So I've done these calculations already. There it is. You can verify this if you want to. And this is where I start. I'd start using Sage Math for this. Okay, so this is our best non-solution. Okay, so let's try it again. Let's see how good this is. So 2, 3, 4. Okay, so the best we saw so far was m equals 1, b equals -1. And that gave us the magnitude, an error vector with magnitude 3. Okay, but we've got a new challenger. M equals -1/2, b is 4. Let's see, so -1.5 plus 4 is 2.5. -2 plus 4 is 2. -2.5 plus 4 is 1.5. So I'm getting these predicted values by using that. So in this case, the error vector is 2, 3, 1. And the magnitude of the error vector is, if you work out the arithmetic, it's about 1.2. Okay, so 2 things I want you to notice is get back to black. It's approximately equal to. Okay, so this is a better non-solution than m equals 1, b equals -1. And even better is this is the best, in my sense, non-solution. Okay, so if we look at our data, there is 3, 2, 4, 3, 5, -1. We should talk a bit about what this means. You might, I don't know if you've heard this phrase before or not. This is referred to as the regression line. Does that sound familiar at all? Okay. It's a common term. You'll see it again. And what we did was, these are the individual errors. So we minimized the sum of the squares of the individual errors. Because this is an important concept in machine learning and in statistics. But what's interesting is there's another problem that we solved here. So let's put it this way. We found another way to calculate projections as well. Okay, so if I go back to this picture, where was it? Okay, so remember, what we're trying to do is solve this system of equations. In other words, we're trying to find the input that produces the projection as an output. Okay, so if we apply A to that input, we actually get the projection. So let's do that. Let me rewrite the problem. Yeah. Okay, so we're in 3-dimensional space. There's a basis for W. Find the projection of Oh no, actually, let's do it this way. So we're in a three-dimensional space. W is a two-dimensional subspace. We want to find the projection of 2, 3, 1 on to W. Okay, so first, find X such that then calculate okay, so from above, we got that X vector is negative 1/2 and 4. And then we'll do this calculation. So this is negative 1/2 we actually did this calculation already, I think. Yeah, so this is 2.52 and 1.5. So this was actually what the predictor predicted. So here, make that box look nicer, is our answer. The projection of 2, 3, 1 onto W. Let's try one more of these, and then we'll do this on. Yeah, then I'm gonna. Yeah, we got more stuff I want to do. So new problem. Bless you. Let's do it this way. So I'm giving you a two-dimensional subspace in R3, and I want you to find the projection of some given vector onto that subspace. Okay, let's start with A. Okay, so here's my system of equations that doesn't have a solution. convert it to the matrix form. And solve a different set of equations. What we do is we transform this into a different set of equations. Is that right? 14. Oh, no, actually, it's wrong. 14 goes there. This would just be the sum. Oh, that should just be 6, 18. Let me just double check that. That's going to be a 3, 9, 10, 14. Yeah, that's right. Just an aside is, hopefully you can see this always works out, is these two entries match. That's going to be important once we get to chapter 8. A similar thing happened here. Is these two entries matched? Okay, so there's our system. Chapter 2, we learned we can solve that by moving the matrix to the other side as an inverse. So that's 1 over 42 minus 36. I'll let you do the calculations, and we end up with -4, 3. So the best non-solution is xy is negative. Actually, let's write it this way. So x is -4 and y is 3. Okay, then for b, let's remember what was it? It was 1, 1, 1. Okay, so I guess in general, yeah. So what we wanted to do is solve this equation. So we found that the solution is x equals -4, y equals 3. So if I do 1, 1, 1, 1, 2, 3, -4, 3, I get the projection of 0, 0, 6 onto W. And there's the projection. Let's see, I think, I know this is written out, but I think this is going to work. So I can't tell you how many times we've done this problem, one similar to it. If you got the line y equals 2x, we've got that 515 vector is given. And we want to find that vector. Okay, so hold on, let me think for a minute. Actually, let me do this in general first. Okay, so the general problem is we're finding the projection of B onto the column space of A. So first, solve AX equals. So we're going to solve this system of equations. In other words, we're solving a transpose AX is a transpose B. Oops, it's B. If we're going to talk more about this probably on Wednesday. So if A transpose A has an inverse, then the solution is this. The projection is AX, which is A transpose A inverse A transpose B. Okay, so if we call this W, everything in W can be written this way. That's the vector description of W is the vector 1, 2. This is our A matrix. So we just worked out the general formula. A is 1, 2. A transpose A is 1, 2, 1, 2. Inverse A transpose is 1, 2, and B is 515. Okay, this is kind of interesting. This is just a number. This is a dot product. Be a little bit careful. Actually, no, scratch that. And save that to the end. Okay, so this is 1, 2, 2, 4. Let's see, so that is 5 and 30. It's 35. Is that 7? Let's see, 5 and 30. It's 35, yeah. So that's 10. That was 7, 14. And notice I was careful with the order. I calculated everything. Here's another way to calculate the matrix that projects onto y equals 2x. So we can actually calculate the projection matrix. Actually, I guess work out the general formula. So this is the matrix that projects onto column space of A. So yet another way to solve that problem. Okay. Let's do one more thing. It's sometimes the model predicts that the data should be quadratic. In other words, the data points satisfy an equation form. So your model, I mean, the idea is you've got messy data. There's a simple reality behind it. Your messy data is the real data plus some noise. And the model is going to predict a simple function that'll explain the real data. So sometimes it's linear. We just talked about that. Sometimes it might be quadratic. So maybe this is the form the model expects it to have. So we've got -1.80814,216. So we want to find the best quadratic function that fits the data. In other words, we want an equation that looks like y equals ax squared plus bx plus c. So plugging into the expression or the system of equations that it should satisfy gives me this inconsistent system. This I can turn into matrix form. I got 4 minutes. I'm going to switch this over to Sage Math and show you what I would do. So you can do it by hand. You've got the tools. This would just be an easier way to do it. Pin here, copy this down. Oh, okay, already. A is the matrix. Yeah. Now where do my square brackets go? Is this? Oops. Gonna do it this way. You're gonna have time for this? Nah, too close to the end. So this is where we're gonna pick up on Wednesday's lecture. Is I'll start with this system and I'll show you how we can use Sage so you don't have to do all the calculations by your hand. Okay, then some homework hints. And oh, do you know there's a test next week? There's a test next week, Wednesday. So the topics are chapters 3 and 5. I'll finish chapter 5 on Wednesday, give you some homework hints. Monday the following week will be a review. Wednesday will be the exam. Oops, let me.
Next week on Wednesday.
Right.